1879, at Johns Hopkins University, a young PhD student named Edwin H. Hall, with the help of Professor Henry Rowland, discovered that a small transverse voltage appeared across a current-carrying thin metal strip in an applied magnetic field. This is significant because at the time, electrical measurements provided only the product of carrier density and mobility. But with this discovery, which would later be known as the Hall Effect, we could directly measure the carrier density. In his paper on a new action of the magnet on electric currents, Hall argued if the current was affected by the magnetic field, then there should be a state of stress, the electricity passing toward one side of the wire. When a magnetic field is applied to an electric current consisting of electrons, holes, or ions, the current experiences a Lorentz force. The charge carriers are forced to the surface of the conductor, which results in a charge buildup and increased current density on one face of the conductor. A Hall voltage can then be measured perpendicular to the current. The Lorentz force is an application of the right-hand rule. It states that the force equals the cross product of the carrier velocity in the applied magnetic field added to the electric field multiplied by the electronic charge. In a steady state where we set the force equal to 0, we see that the y component of the force equals the negative of the x component of the carrier velocity multiplied by the z component of the magnetic field. This also equals the Hall voltage divided by the conductor width. The transverse force applied to the current is the Hall voltage, VH. With the equation for Hall voltage and the equation for current, we see that the Hall voltage equals the x component of the current times the z component of the magnetic field divided by the number of charge carriers times the electronic charge times the thickness of the conductor. With some magical algebra, we see that the Hall voltage equals -1 over Ne, which also equals the Hall voltage times the conductor thickness over the current times magnetic field. On previous slides, we saw the Hall effect in metals. Now let's look at the Hall effect in semiconductors. Here it can be a bit more complicated because of the presence of electrons and holes, each with their own mobilities.
Now let's talk about sample preparation for Hall effect measurements. The quality of the sample would rely on the uniformity of thickness, the presence of holes in the sample, the homogeneity of the material, the contact location of the probes, as well as the area of probe contact. We use the Van der Pol technique when measuring for the Hall effect. There are various ways to construct the sample, but the preferred one is called the cloverleaf, as can be seen on the diagram. We could also use a square or rectangular construction, however, it's acceptable but not preferred. Through his experiments, Van der Pol deduced that there were actually two characteristic resistances, Ra and Rb, in a given sample. He equated them to the velocity and the current as given in the below equations. Ra and Rb can also be related to the overall sheet resistance, Rs, through the Van der Pol equation. And using all of the given variables, we can calculate the bulk electrical resistivity. The overall objective of the Hall measurement in the Van der Pol technique is to determine the sheet carrier density, N sub S, by measuring the Hall voltage, V sub H. The Hall voltage measurement consists of a series of voltage measurements with a constant current and a constant magnetic field applied perpendicular to the plane of the sample. This can be easily demonstrated in the figure given below. As can be seen here, we obtained the data from our sample. The results give us the bulk concentration, the mobility, and the sheet resistance, all of which we were trying to find in the first place.
A Hall effect sensor is a transducer that varies its output voltage in response to a magnetic field. Hall effect sensors work by measuring the Hall voltage across two of their faces when you place them in a magnetic field. There are two circuits that compose a Hall effect sensor. The bias circuit applies a fixed voltage to the top and bottom terminals of the semiconductor material, whilst a measurement circuit senses a voltage between one side of the semiconductor material to another. We know that a magnetic field has two important characteristics: flux density and polarity. When the magnetic flux density around the sensor exceeds a certain preset threshold, the sensor detects it and generates an output voltage called the Hall voltage. The resultant voltage potential across the width of the conductor is called the Hall voltage and can be measured by attaching two electrical contacts to the sides of the conductor. With a known magnetic field, its distance from the Hall plate can be determined. There are two types of Hall effect sensors, including digital and linear sensors. A digital Hall effect sensor produces a constant Hall voltage when the field strength reaches a certain amplitude and/or polarity. There are many different threshold device configurations, such as latching devices which turn on when a positive field strength reaches the threshold, but only turn off under a negative field of the same strength, or devices which turn on when only a positive field reaches a certain threshold and are off otherwise. Analog Hall effect sensors produce a Hall voltage proportional to the strength of the magnetic field around it. The orientation of the surrounding magnetic field determines the polarity of the voltage swing. This is usually applied in music applications. Hall effect sensors are cheap, robust, reliable, tiny, and easy to use, so you'll find them in lots of different machines and everyday devices, from car ignitions to computer keyboards and factory robots to exercise bikes. However, they provide a much lower measuring accuracy than Hall probes. Hall probes are essentially ramped up Hall sensors optimized into a smaller apparatus. A Hall probe contains an indium compound semiconductor crystal, such as indium antimonide, mounted on an aluminum backing plate and encapsulated in the probe head. The plane of the crystal is perpendicular to the probe handle. Connecting leads from the crystal are brought down through the handle to the circuit box. Hall effect probes are more expensive and sophisticated instruments used in scientific laboratories for things like measuring magnetic field strength with very high precision. The Hall probe is a magnetic field sensor that passes electrical current when the sensor is perpendicular to a magnetic field. The stronger the magnetic field, the more current it passes.
Our references! Oh boy!